Welcome to an introduction to real analysis. We continue with Chapter 4, Section 2, the mean value theorem. Now, earlier, back in the sections on continuity, we talked about absolute maxima and minima of functions. These are the so-called tallest peaks or lowest valleys in the entire mountain range, the absolute highest and lowest values that a function takes. But what about peaks of an individual mountain within the range or the bottom of an individual valley? The derivative, it's a local concept. It's a limit as x approaches a point. It only looks near that point. Is likened to walking around in a fog. It doesn't tell you what's happening anywhere but exactly where you are. So it can't tell you if you're on the highest peak of the entire mountain range, but you can tell if you are at the top of a peak you're currently standing on. So here's a definition. Suppose S is a subset of the reals, f is a function with that domain. The function is said to have a relative or local maximum at some point C if there is a delta, so that for all points in the domain, if you are within delta of C, then f of x is less than or equal to f of C. So for all x's nearby to C, f of x is less than or equal to f of C. That is called a relative or local maximum. Similarly, you can define a relative or local minimum just by reversing the inequalities. So let's establish a lemma. Suppose f is differentiable at some point that is a local maximum or a local minimum. Then the derivative must be 0. So we'd like to show that if you have a derivative at a local max or min, the derivative must be 0. So suppose f has a local maximum at C. Then minus f has a local minimum and vice versa. Because minus signs, or multiplication by minus 1, may be factored out of a derivative, and of course negative 1 times 0 is just 0 itself, we really only have to prove this result regarding local maxima. Okay, so at any particular point that is a local max, we're going to compute various secant slopes. And we're going to utilize the fact that we're at a local max to establish some inequalities for these slopes. So let's assume we're at a local max. Now, if we are very close to C, but not exactly equal to it, because f of x is less than or equal to f of c, we were at a max at f of c, we have that the numerator of our difference quotient is not positive. However, if x is to the left of c, the denominator is negative, whereas to the right of c, the denominator is positive. So this difference quotient is non-negative to the left of C and not positive to the right of C. Summarized like this. So we've established that our difference quotient cannot be negative to the left of C, but cannot be positive to the right. So if the following limits exist, they have to obey the same inequalities. The limit as x approaches C from the left cannot be negative, but the limit as x approaches C from the right cannot be positive. We assumed, however, that f prime at C exists, so both of these limits exist and they have to be equal, so the only possible value is 0. Okay, for a differentiable function, any place where f prime of C equals 0 or does not exist is called a critical point. So the previous theorem states that a relative minimum or maximum at an interior point of an interval has to be a critical point. Now, if you have taken an elementary calculus course, you sort of have this memory that to find the min and max of a function, you find all the critical points, and then you also have to test the endpoints of an interval just by seeing what the values are to find the biggest and smallest value. Now, if the derivative at an endpoint is not defined, they're automatically critical points, but we specifically defined derivatives at endpoints. The previous lemma was very specific about only applying to open intervals, in essence to get around this issue. Let's move on to Rolle's theorem. Suppose a function has the same value at both endpoints of an interval. Then, intuitively, we think there should be a max or a min somewhere in between. And then, at such a max or min at an interior point, the derivative would be 0. So this is what Rolle's theorem says. If you have a function whose value at a and b are equal, then you can find an interior point where the derivative is 0. Here it is formally stated. Suppose f has domain, the interval from a to b, including its endpoints. Assume it's continuous, differentiable on the open interval from a to b, and its value at the left and right endpoints are equal. Then there is some point in the open interval from a to b where the derivative is 0. Proof is not bad given all the pieces we've put together up to this point. Since the function is continuous on the closed interval with the endpoints, by the extreme value theorem, there is in fact an absolute max and absolute min. If both the absolute max and min are at the endpoints, because the value of the two endpoints are equal, you would be concluding that the max and min values of the function are equal to each other, which would imply the function is constant. And we already know that a constant function has zero derivative. It's a quick direct proof that we didn't technically do as an example. I believe it is an exercise. So if you have both max and min happening at endpoints, the derivative is zero everywhere. Otherwise, at least one of the max and min occurs at an interior point and therefore is a local max or min at an interior point. What we just showed is that if you have this situation, a local max or min at an interior point, the derivative there must be zero. Now in Rolle's theorem, we absolutely had to assume that f had a derivative everywhere on the open interval from a to b. So an absolute value function, for example, is continuous from -1 to 1. But there is no place where the derivative is zero because the derivative would fail to exist at one point in between -1 and 1. We can, however, create an extension of this theorem without the assumption that the value at the endpoints are equal to each other, without the assumption that f of a equals f of b. And this is what's known as the mean value theorem. Suppose f is a continuous function on the interval from a to b, including the endpoints, and has a derivative everywhere from a to b, not necessarily including the endpoints. Then there is a point on the interior where the value of the derivative is equal to this difference quotient looking thing, f of b minus f of a over b minus a. The proof is fairly straightforward, having already established Rolle's theorem. So here is a picture that gets across the idea. If you have a nice curve from a f of a to b f of b, there is at least one point in between where the tangent slope is equal to this overall secant slope. So f of b minus f of a over b minus a is the slope of the line connecting those 2 points, a f of a to b f of b. And we just want to find at least one interior point where the value of the derivative is equal to this secant slope. So all we have to do, let's summarize that the value we're looking for, f of b minus f of a over b minus a, we're just going to call it m. We're going to make a new function called g of x, which is simply f of x minus m times the quantity x minus a. Okay, mx is continuous, it's a line, and it's differentiable everywhere, so g, f of x minus this line plus the constant ma, is continuous on the closed interval and differentiable on the open interval. And we simply compute g of a is equal to f of a, and g of b, after working through the computation, f of b minus m times b minus a, but what was m? It has this denominator b minus a that cancels out, and you recover f of a. In other words, g of a equals g of b. So g is now a function on which we can apply Rolle's theorem. So there must be an interior point where g prime of c is equal to 0. Great, we found a place that g prime has to be 0, but here's g of x. So let's take its derivative. What is the derivative of g? Well, it would be f prime minus the derivative of mx plus the derivative of ma. Of course, the derivative of mx is minus m. The derivative of ma is 0 since it's a constant. So setting g prime of c equals to 0, we find that f prime of c must equal m. The mean value theorem is a nice little thing to present. It has the distinction of being able to be cited in court. So when police measure speed of cars by aircraft or with camera readings, what they're typically doing is measuring the time it takes for a vehicle to go between two pre-marked locations. So the mean value theorem then states that if the car covered a certain amount of distance in a certain amount of time, the average speed must have actually been attained at a certain point. That is, of course, assuming that the path your car takes is continuous and differentiable. There is a generalization, by the way, of the mean value theorem, which we will not prove. It's exercise 4.2.15. But basically, overall, if you can show that a car traveled 80 miles in 1 hour, you simply say at some point it had to be going at least 80 miles an hour, which is above the speed limit. Intuitively, it makes sense, but hey, it's the mean value theorem, and it is, thankfully, true. So here is that extension of the mean value theorem. We're going to state it but not prove it. The proof is left as an exercise. This is Cauchy's mean value theorem, otherwise known as the second mean value theorem. Suppose f and g are two functions, both of which satisfy the hypotheses of the mean value theorem, continuous on the closed interval from a to b, differentiable on the open interval from a to b. Then there is an interior point where f of b minus f of a times g prime of c equals f prime of c times g of b minus g of a. Often this is written by dividing this difference to one side and this derivative to the other, in which case you would have f of b minus f of a over g of b minus g of a equals f prime of c over g prime of c. Again, we're not going to prove it here. It is an exercise. So let's talk about applications of the mean value theorem. What we're going to see is pretty typical where the mean value theorem is concerned. We're going to want to not have to talk about derivatives, in other words, limits. We would rather talk about a nice explicit secant slope computation. Okay, and now getting those two things equal to one another is exactly where the mean value theorem comes in. So our first example is to solve the differential equations. In other words, what functions solve f prime equals 0? So suppose you have an interval and a function is differentiable, but the derivative is always 0. We claim the function must be constant. Can we prove it? Now let's suppose to the contrary you have a non-constant function. So there are 2 points in the domain with a less than b without loss of generality where the value of the function is not equal. Now, since the function is differentiable on the entire interval I, it is differentiable on this interval. Since it's differentiable, it's continuous, but also it's differentiable on the open interval. In other words, f satisfies the mean value theorem on this interval from a to b. So there must be a point in between where the value of the derivative is equal to this nice straightforward quotient that doesn't have a limit. However, f of b is not equal to f of a, so this is not equal to 0. So under the assumption that a function is not constant, there must be at least one point where the derivative is 0. In other words, if the derivative is always 0, the function must be constant. So let's talk about that. We know what it means for a function to stay constant. Let's look at increasing and decreasing functions. Remember that a function is increasing, and you can also say strictly increasing, if whenever you have an inequality in the domain, the same inequality, possibly introducing equality, is introduced in the range. If you do not introduce possible equality in the range, that's what's called strictly increasing. Okay, decreasing and strictly decreasing defined analogously. We're going to prove a result totally familiar to people who've taken an elementary calculus course. But now we can prove it. Specifically, let I be an interval and f be differentiable. Then f is increasing if and only if the derivative is never negative, and f is decreasing if and only if the derivative is never positive. So can we prove it? As we've already remarked, going from increasing to decreasing functions and back and forth can be accomplished by multiplication by the constant -1, so we're just going to prove the first thing about increasing functions. Assume that f is increasing, then for any x not equal to c, this quotient cannot be negative. Why not? Well, if x is larger than c, the numerator is non-negative because the function is increasing and the denominator is assumed to be positive, achieving this inequality. Similarly, if x is less than c, while the denominator becomes negative, because x is increasing and x is less than c, this numerator is also not positive. So regardless, we get this stated inequality in the middle of the page. Now we can simply take a limit as x approaches c to recover the derivative at c, and we get bigger than or equal to 0. So if f is increasing, the derivative is certainly not negative. We did not need the mean value theorem here, simply the definition of the derivative. Now let's assume that the derivative is never negative on our interval I. Assume to the contrary the function is not increasing. Now we are not assuming that the function is decreasing. The negation of increasing is not the same thing as decreasing. The negation of increasing is just that there exists a single pair of points where an inequality is flipped. x1 is less than x2, but f of x1 is not less than or equal to f of x2. In other words, f of x1 is bigger than x2. But now, we have a function continuous on the interval from x1 to x2 and differentiable on the open interval. So we may apply the mean value theorem to say there is some interior point where f prime of c is equal to f of x2 minus f of x1 over x2 minus x1. But our numerator is negative and our denominator is positive. So we end up with a point where the derivative is negative. That contradicts our assumption that the derivative is never negative. So a little discussion is in order. One direction of the previous proof, that an increasing function has a non-negative derivative, followed just by using the definition of the derivative. You can prove that direction by citing the mean value theorem, but it's not as straightforward, and it has a potential pitfall that many students don't properly take care of. The other direction, however, that a non-negative derivative must imply an increasing function, not necessarily strictly, incidentally, but increasing, required using the mean value theorem. So now we'll show that a similar result for strictly increasing decreasing functions is possible, but it's not if and only if. It only holds in one direction. Note, by the way, that x cubed is a strictly increasing function, but its derivative does equal 0 at one point. So it is not true that if you have a strictly increasing function, you must have a strictly positive derivative. That's the direction that fails. So prop 4.2.8, suppose you have a differentiable function on an interval. If the derivative is strictly positive, then f is strictly increasing. It doesn't go the other way. Strictly increasing, you can have derivative be 0 at certain points. Similarly, if the derivative is strictly negative, then f is strictly decreasing. Now, the proof of the previous proposition is an exercise. We're not going to go over it. Another application, however, of the mean value theorem is the following result about where extreme values can possibly be. This is sometimes called the first derivative test. The result is stated for an absolute min and max. Now, to apply it to a relative min and max, restrict f to a little interval around a point. Remember, any local or relative max or min on a sufficiently small interval is an absolute max or min. So here's that proposition. Let f be continuous on an open interval. Let c be an interior point. And suppose f is differentiable at least from a to c and c to b. If f prime is less than or equal to 0 to the left of c, but bigger than or equal to 0 to the right of c, then c is an absolute minimum, whereas, in contrast, if f prime is bigger than or equal to 0 to the left of c, and less than or equal to 0 to the right of c, then c must be an absolute max. How's this proof? Honestly, not so bad. We're only going to prove the first one. Again, multiplication by -1 gets us back and forth. So we're just going to handle absolute mins. We're assuming f prime is less than or equal to 0 on the interval from a to c. In other words, it's decreasing from a to c. Now pick any point in between a and c and let y be in between x and c. Now, since y is larger than x, and our function is decreasing on this interval, f of x is bigger than or equal to f of y. But f is continuous on the entire interval from a to b, meaning f of c is the limit as y approaches c of f of y. Since this limit exists, the one-sided limit is equal. However, if y is less than c but bigger than x, which would be the case as y approaches c from the left, f of y is less than or equal to f of c. So this limit, f of c, is also less than or equal to f of x. Similarly, f of c is less than or equal to f of x for all x to the right of c. So we have achieved that c is actually an absolute minimum. Okay, f of c is less than or equal to all values of f of x sufficiently close. Loosely stated, the previous proposition says, if your derivative goes from negative to positive, if your function goes from decreasing to increasing, then you had a local min. The converse doesn't quite hold. There are functions that have absolute maxes or mins where the derivative doesn't go from one sign to the other. And an example will be developed quite shortly. But another used application of the mean value theorem that you may have seen before is the following result regarding differentiability at endpoints. The proof is left as an exercise, but we will state the result here. So here's the proposition. Suppose f is continuous and differentiable on the open interval from a to b, continuous at the left endpoint. Similarly, the derivative has a limit as x approaches the left endpoint. Then the derivative at the left endpoint is the value of that limit, with a similar result for the right endpoint. Again, we are not going to prove this. It is left as an exercise. Okay, let's talk. A differentiable function has to be continuous. We established that back in section 4.1. The derivative, however, does not have to be continuous. This is a fairly common intuitive error students make. A function can have a derivative without that derivative being continuous. Example 4.2.12 will develop such a function. The derivative exists everywhere, but does have a discontinuity. However, while not necessarily continuous, derivatives do satisfy a result very similar sounding to the intermediate value theorem. So here is Darboux's theorem. Suppose f is a differentiable function from a to b. Suppose y is a value in between f prime of a and f prime of b. Whichever one is bigger, squeeze y in between. So y is an intermediate value for the derivative of f. Then there is a point somewhere in between a and b where f prime achieves that intermediate value. In other words, the intermediate value theorem for derivatives. Again, derivatives do not have to be continuous, so you cannot simply cite the intermediate value theorem. Well then, how will we prove it? More or less the same way we proved the mean value theorem. Specifically define a new function g to be f of x minus yx. Remember, y is just a constant in this setup to Darboux's theorem. So g of x is our differentiable function f minus a constant times x. So its derivative is just f prime minus that constant y. We were trying to find a place where f prime equals y. Now note, if f prime equals y, g prime equals 0, and vice versa. So let's just assume that f prime of a is less than y is less than f prime of b. We had to make one of these two assumptions to write down a chain of inequalities. It doesn't really matter which one you pick. The proof will be essentially the same in both cases. Now g is continuous on the interval from a to b. Continuous functions have absolute maxes and absolute mins. So this function g has an absolute max and absolute min between a and b. However, assuming f prime of a is less than y, g prime of a is negative. So for all x in some little interval from a to a plus delta, we have to have that this difference quotient is negative. If the limit as x approaches a is negative, then as x gets sufficiently close to a, all such values must be negative. However, since x minus a is positive on that interval, we conclude that g of x minus g of a is negative. In other words, g of a is bigger than g of x for all x sufficiently close to a. So a cannot be the absolute minimum of g. Similarly, we find that b is not the absolute minimum of g either. So g is continuous, it must have an absolute min, but that absolute min cannot be either endpoint a or b. Therefore, g must achieve its absolute minimum somewhere in the middle, but g is differentiable. So wherever it achieves its absolute minimum at an interior point must have derivative 0. G prime of c is equal to 0 is exactly the same as saying that f prime of c is equal to y, and we're done. We already saw that there exist discontinuous functions that satisfy the intermediate value property. Refer back to example 3.3.12. Now it's hard to imagine, but there are functions that are differentiable everywhere, but the derivative is not continuous. We will present such an example now. Here it is. Here is a function given by the square of x times the sine of 1 over x, at least when x isn't 0, or just equal to 0 when x is 0. For x not equal to 0, then we can make a little interval around x that doesn't include 0. This is just the square of a product of a differentiable function with a composition of two differentiable functions. We would simply compute the derivative through all of our familiar rules. And there it is. It's not particularly pretty, but that is f prime, at least not at 0. The real issue is computing the derivative at 0. Okay, let's just go through the definition. F prime of 0 is the limit as x approaches 0 of this difference quotient. Of course, f of 0 is 0, and I can ignore both of these. What is f of x over x? I'm going to cancel one of the x's from this x squared, and we get x times sine squared. But sine squared is bounded between 0 and 1, so I can squeeze this multiplication by x as x approaches 0, and this limit must be 0. So f prime of 0 is 0. So now we're going to just state what is f prime. We computed it away from 0, we computed it at 0. Here's f prime. It's this whole expression away from 0, and at 0 the derivative simply equals 0. We claim that this derivative is not continuous at 0. So we're going to take two different sequences, xn and yn. 4 over 8n plus 1 times pi, or 4 over 8n plus 3 times pi. So what's 1 over xn and 1 over yn? Quite nicely expressed here. 2 pi n, since they're about to be fed into sines and cosines, the appearance of 2 pi n is pretty straightforward. But then you get a pi over 4 or a 3 pi over 4. Now both xn and yn go to 0, right? As n goes to infinity, both of these are collapsing to 0. However, f prime at xn is constantly minus 1, and f prime at yn is constantly plus 1. This is simply taking these 1 over xn's and 1 overyn's and plugging them in here. Okay. The sine of pi over 4 and the cosine of pi over 4 and the sine of 3 pi over 4 and the cosine of 3 pi over 4, just hack it all out. You will find for every xn, f prime is minus 1, and for every yn, f prime is plus 1. So we can't have continuity at 0. I have two different sequences converging to 0. On one, f prime is constantly minus 1, on the other, f prime is constantly plus 1, and f prime of 0 is neither plus or minus 1. So f prime is not continuous at 0. So here is our function that has a derivative, but the derivative is not continuous. Often it's nice to assume a function not just has a derivative, but that the derivative is continuous. So if you have a function that has a derivative which is continuous, we call that continuously differentiable. That's what the term means. Common notation for this is C sub 1. The set of continuously differentiable functions on a set is called C sub 1 of that set. So the set of functions on I whose second derivative exists and is continuous is C sub 2, and so forth. C sub 3 has a third derivative and the third derivative is continuous, etc. Now, we're not really going to use that notation, but in some other branches of mathematics, it pops up a lot. So if you see C sub something of a set, that often means has that many derivatives and that derivative is continuous. What did we talk about here? The mean value theorem doesn't necessarily look all that important at first, but it's something we're going to cite quite a lot. The picture of the mean value theorem is that there has to be a point in an interval where the tangent slope equals the average or mean rate of change, hence mean value theorem. But the real utility of the mean value theorem is that it allows us to translate a global property, an average rate of change over an interval, into something local, the actual derivative at one point. The trade-off is you simply know that such a point exists. You don't necessarily know how to find it. Okay, but that is how we're often going to cite the mean value theorem. Take a global quantity, an average rate of change, and represent it as an instantaneous rate of change or a derivative at a specific point, even if we don't know where it is exactly.